right. So today is the sorry, I see the transcription going on the screen. It can be amusing to read the transcript. It's really bad, or I just don't talk so good. This is for those of you who took Math 561. This is the last material that is a retread from that class. We're going to be finishing off chapter 3. So this number of matrix measure sensitivity of x equals b problem, but in order to even define a condition number, I need to talk about norms, vector and matrix norms. There's a section about those in Appendix B of the book that's all about a review of linear algebra. Okay, so let's start out with vector norms. Now, the idea behind norms is to give a notion of magnitude of something. Simplest norm of all is absolute value of a number. So the idea is to generalize the concept of absolute value of a number in some way to vectors and matrices. So something that would be familiar to most from calculus, you have a vector, say, an Rn. So the magnitude of a vector, which depending on the book you're using, may be written using just the same old absolute value bars or the double bar. I prefer the double bar just because it looks cooler. Would be the square root of sum of squares of all the components, also known as Euclidean length. And it is one of the ways of describing the magnitude of a vector that we'll be using, but there are other ones too that are quite helpful. Okay. Now, first I'm going to focus on what is it that any vector norm, what properties do any vector norm have to have? So a vector norm that's described by closing a vector in a set of double bars. The dot there is a placeholder for whatever vector we're taking the norm of. And describing it as a function from some vector space V. And we're mainly interested in a vector space such as Rn. In fact, I think it's all we need to deal with in this class. But concepts apply for general vector spaces. So a norm is a function whose domain is a given vector space, usually Rn, and its range is just a set of real numbers. V is a vector space. Must satisfy these properties we call a norm. Okay. First, for any vector in your space, the norm cannot be negative. In fact, it is strictly positive unless the vector in question is 0. So the norm is equal to 0 if and only if vector x itself is 0. So it makes sense. If you're talking about magnitude, a 0 vector should have a magnitude of 0. Any other non-zero vector should have at least some non-zero magnitude. So often if a function that you're not sure if it's a norm fails to be a norm, usually because it doesn't satisfy this property. Second, if you scale a vector by some constant vector c, then that scales the norm by the absolute value of that constant. Makes sense, because if you're doing it to a vector, all you're doing is you're changing its length. Finally, triangle inequality. The norm of sum must be less or equal to the sum of norms. So any function defined in a vector space, the real numbers that satisfies these three conditions, you're allowed to call it a norm. Okay. So now, let's look at some specific examples of norms. In fact, our focus is going to be on a family of norms called the P norms, also written as I see that trouble writing today, or LP norms. That's a fancy L there. Right. Okay. So they all have a common definition that we identify which P norm it is using a subscript. So P is a number in this case. And is defined to be the sum, and we're assuming it's. I'm going to write this definition so that it works for real or complex vectors. So we take the absolute value of each component of a vector and we raise it to the P power. So, and the P can be odd, for instance, so that's why we have some values needed, and certainly if the vector is complex. We add them all up and then we raise the sum to the 1 over P power. So whatever P you choose, that's a P norm. That's how P norm is defined. Okay. So, and there are really only 3 values of P we care about in this class. In fact, I don't think I've ever dealt with other values of P besides these, at least not for vectors in Rn. You could define a norm of a function of x, like f of x, where instead of a sum, you have an integral. Like, so the LP norm of a function would be integrating a function raised to the P power on some chosen interval, and then you raise the integral to the 1 over P power. So it's, yeah, so it's like a summation, but infinitely many terms. It can give the integrals a limit of Riemann sum. And in that case, I've seen some unusual choices of P. Like I've actually worked with P equal to -1/2, for instance, but here are values of P that we'll deal with. Well, probably shouldn't have written it this way, P values of interest, because this has absolutely nothing to do with the P value from statistics. I probably should phrase that differently. P is equal to 1. So all that is, the 1 norm, is just a sum of the absolute value of all the components. P equals 2. That's what we've already seen. That's Euclidean length. Okay. Often this one is preferred because in general, a norm is a continuous function of the components of a vector. But when it's a 2 norm, we can go further, say that the 2 norm is a differentiable function of a component, which is nice if you're trying to find a minimum or maximum of a 2 norm, using techniques from calculus where you take a derivative, set it equal to 0 and all that good stuff. Okay, and then the other P value we'll make use of is infinity. What happens is as P increases, the largest component of the vector is given more weight, makes more of a contribution to the norm. So if you take that to its extreme, the infinity norm of the vector is just the maximum absolute value of all the components. Okay. So real cut and dry there. So as an example, if I define my vector to be 1, 2, minus 3, then the 1 norm of x is 6. 2 norm of x would be 1 plus 4 plus 9. So it's the square root of 14. So 3 point something. And then the infinity norm of x is 3. So you notice that as the value of P increases, the norm decreases. And that's something that holds true in general. Like I said, because larger components get more and more weight. So by the time you get to infinity, the other components are making no contribution to the norm at all. So that's why we see this decreasing trend here. Actually, just work on another example, because this is something that comes up now and then. If I have a vector that is all ones in n-dimensional space. So we have n ones here. So 1 norm of x is equal to n. 2 norm of x would be square root of n. And the infinity norm would just be 1. So in general, the P norm would be n raised to the 1 over P power. So I can make that statement in general. So as P goes to infinity, we end up with basically it's like n to the 0, which is 1. Okay. All right. Do you have any questions at this point? Including from online. You all can chime in if needed. All right. So one inequality of interest from the Elder inequality that the so I'm going to assume that the vectors x and y are real, or an Rn. So x transpose y under that assumption is the dot products. Also, dot product is an example of an inner product. There are many inner products, but this is most frequently used one, I guess. Is less than or equal to the P norm of X times the Q norm of Y, provided that 1 over P plus 1 over Q is equal to 1. Now, a special case of that is of interest. P and Q are both equal to 2, so we'd have 1/2 plus 1/2, so that works. Then we get the Cauchy-Schwarz inequality that you may have seen before. That is that the absolute value of the dot product of X and Y is less than or equal to 2 norm of X times the 2 norm of Y, which makes sense when you consider that the dot product of X and Y is equal to 2 norm of X times 2 norm of Y times the cosine of the angle between X and Y. So that's what theta is. Angle between X and Y. So, and certainly, of course, cosine can't be any greater than 1. So the dot product is maximized when X and Y are parallel or pointing in the same direction, in which case cosine theta would be 1. So that's where you get equality. Now, in the notes, I have you think this is as a proof by taking this formula from a dot product for granted. There is a proof in the notes of the Cauchy-Schwarz inequality for real vectors that doesn't use that. And as much as I enjoy doing that, I want to make sure I get through all the notes. So y'all can look at that later. But I will tell you about a prank I pulled once on my Calculus 3 students over the dot product, because so the dot product is commonly taught in here in Calculus 3. So I had introduced the Cauchy-Schwarz inequality that you see here. And then I pointed out special cases of where theta is equal to 0, so the inner product is equal to the product of norms, or when theta is equal to pi. So in that case, if X and Y are pointing in opposite directions, then X transpose Y is equal to minus the product of the norms. And so that first case, I actually gave it a made up name in cahoots with a friend of mine out in Oregon who at the time was a community college math instructor, and her last name is Tilia. So I called it the Tilia equality. And I just totally made that up and I wrote that in her notes. And so somewhere in some Calculus 3 notebook, there's this made up equality mentioned. So would be funny if it spread, but but the thing is, I was a Wilson. I only did it that 1 year. I've taught the class a few more times and I haven't brought it up since, but actually teaching Cal 3 now. Okay. All right. Okay. All right. Now, am I doing on? certain more important things I want to make sure I cover today. Right. Okay, so, and a lot of reasons one needs a vector norm. But what's of particular interest to us has to do with convergence. Soon we're going to be seeing, like later on in this semester, we're going to be seeing iterative methods for solving AX equals B. And norms are useful for defining what it means for a sequence of vectors to converge. Okay. So the sequence of vectors, x0, x1, so on. So the superscript in parentheses is used to as an index, so it's the number of iteration. So a sequence converges to some vector x if the limit, as k goes to infinity, of the norm of a difference between xk and x converges to 0 as k goes to infinity. So we think of the norm, rightfully so, as a distance. The norm of the difference of vectors is a distance between those two vectors. The distance between xk and x must go to 0. Right. In some norm, I've not specified what norm it is, but as you'll see in a moment, it's actually not going to matter. Okay. Now, it turns out that if this is true, if and only if each individual component of xk converges to a corresponding component of x. Assuming that everything in Rn as usual. So convergence in the norm is equivalent to convergence to component-wise convergence. You can't have one without the other. And this is the case due to the norm of a vector being 0 if and only if the vector itself is a 0 vector. That's why that property of norms is particularly important. Okay. Now, is it a problem that I've not specified norm? Is it a situation where a sequence of vectors converges to a limit in some norm, but then that same sequence of vectors does not converge to that limit in a different norm? At least if you're talking about p norms, there's no way that can happen. This leads to the concept of norm equivalence. If I pick out two norms, however they might be defined, as long as they satisfy the three conditions given in a definition, I'll refer to these generically as the alpha norm and the beta norm. They are said to be equivalent to one another if these norms of a given vector satisfy these conditions. So the beta norm of x must be bounded above by some constant by the alpha times the alpha norm of x, and bounded from below by some other, oops, that should be C2, by some other constant times the alpha norm of x. Some constant C1, C2, and this is actually true for all x in whatever vector space you're dealing with. C1, C2, the constants have to be independent of x. So if two norms are equivalent, then if a sequence of vectors converges, say in the beta norm, it's going to converge in the alpha norm. The rate might be a little different. The actual norms, of course, will be different, but the norms, if one set of norms is going to 0, the other one will too. Okay. And in particular, all P norms are equivalent. Any two P norms, these constants do exist. Finding them might be rather difficult. They make for rather vexing homework problems to find them. Don't worry, I didn't assign any. But I will give some examples. Okay, first, the relationship between the one norm and the two norm. The one norm, and we saw in the illustrated examples earlier, is greater than or equal to the two norm, and is less than or equal to square root of n times two norm. So the constants, C1 and C2, might depend on the dimension of the space. And here, this is two norm versus the infinity norm. So the two norm is greater or equal to infinity norm, less than or equal to square root of n times the infinity norm. And finally, the one norm greater or equal to infinity norm, less than or equal to n without square root times the infinity norm. I can tell you which vectors actually bring about equality for these bounds. For example, if you choose a vector x that is all 0 except for one component that is equal to 1, that would bring up equality for all of these cases. Whereas if you set x equal to a vector of all 1s, then you have equality in these three cases. Okay, might have forget. Wait, I take a vector of okay, the vector of all 1s, the two norm would be square root of n, times square root of n, which is n. The one norm of that vector would just be n. So yes, it is equal. I have something in here, but I know it's more complicated than that. Like, what was I doing? Go figure. But actually, I do have a proof in the notes about showing that the two norm is Not that great. Okay, yeah, showing the equivalence between the one norm and two norm. All right. Sorry, I'm skipping on these things, but I'll make sure the matrix stuff all gets covered and not in a rush. Okay. If time permits, I will circle back though. Okay, actually now I am in a position to talk about matrix norms. Okay. So now it's tempting to give an m by n matrix A. It's tempting to define its magnitude by thinking of this m by n matrix as a big long vector, you know, m times n entries, and use vector norms. That doesn't necessarily work. So we're not going to do that. Well, okay, in one case we will, but not in general. So so a matrix norm, also defined using ANOVA bars, specifies first properties are the essential properties are the same as for a vector norm. The norm of a matrix must be non-negative. Norm of a matrix is 0 if and only if A is a 0 matrix. You scale the matrix by a constant. The scale's a norm by the same constant. You have a triangle inequality. It's all pretty boring. And then there is another property I'd like to add. I'm going to put an asterisk with it though, because it's not necessarily included in the definition of a matrix norm. Some sources might, but it is a property that we like matrix norms to have. And this is called the submultiplicative property. That is that the norm of a product, so assuming that the product, matrix product makes sense for dimensions of A and B, is less than or equal to the norm of A times norm of B. So the norm of a product is less than or equal to the product of the norms. For any norms that we'll be dealing with, this property does hold. Oh, I have fewer pages than I thought. Okay, cool. Yeah, but I'm exactly halfway through the notes. We're exactly halfway through the class period, and I started a little late. So, okay. So the way that I'm actually going to define a matrix norm is in terms of the corresponding vector norm. This is called an induced, also known as a natural matrix norm. The idea is you define the norm of a matrix as the supremum over all non-zero vectors X of a ratio of the norm of AX to the norm of X. So in other words, what is the maximum possible amplification of X you can get due to multiplying by A? So you have a vector X of some length, you multiply by A, you get a new vector of some length. What's the maximum extent to which X's length can be extended by multiplying by A? I think I just said the same thing twice, but it sounded better the second time. That's one way to define it. Another way to define it is we can take the maximum over all unit vectors, vectors of norm one, of just A times X. All right. Then tell me why I have to say soup here and like and not max, whereas I could say max over here. And
Would it be, deal with boundedness?
Partly, yeah. We're actually talking about sets that are bounded and closed, compact.
Yeah.
This is a compact set. So it has a continuous function compact set, max and minimum. It's not compact. So, yeah, and it's kind of a hair splitting thing, but the point I like to make is I feel more like a mathematician that way. No, my advisor, Gene Gollin, I mean, incredible researcher in matrix algorithms. He had this perception that his colleagues at Stanford over in the math department, because he was in computer science, thought of him as a lightweight because he wasn't in the math department. Didn't get like most areas of math. So yeah, I mean, I don't know. Okay, now, so the idea is we choose a vector norm. Now, if A is m by n, this would be a vector norm on Rm. This would be the corresponding vector norm on Rn. So we are using different vector norms of the same type of norm. So for instance, if we're using a p norm, we're using the same p norm in numerator, denominator, and over there. So if a vector norm is an LP norm, so any norm from that family, the matrix norm that we get is submultiplicative, which is a lazy way of saying it satisfies the submultiplicative property, that the norm of the product is less than or equal to the product of the norms. So and we're only going to be dealing with, well, most of the matrix norms we're dealing with are induced by some vector, LP vector norm. So we can take that property for granted. All right. So now I will describe some specific matrix norms. So first we have the L1 norm. So one norm of a matrix A, which is defined as the maximum over all vectors whose one norm is equal to 1. So the sum of the absolute values of the components is 1. A times X. Turns out to be equal to the maximum over all columns of the sum of the absolute values of all the entries in that column. A concise, though admittedly imprecise way of saying it is I think of a one norm as the maximum column sum, but just have to remember that's absolute values. Okay. So I'm going to show you how this formula can be proved. Okay. So I'm going to assume that the one norm of X, which is the sum of the absolute values of all the elements of X, is equal to 1. Okay. And now I'm going to look at, should be a 1 here. I'm gonna look at this one norm of A times X. Using a formula. First for the one norm. So I take the absolute value of A times X, component I, and I add up all the absolute values. But now I'm going to write those components in terms of using a formula for matrix vector multiplication. So I'm going to have sum of it is sum, Aij xj. So that's a formula for component I. And now triangle inequality for scalars. So I'm going to have I can take the sum over j and move that to the outside. Oh, I goofed here. This should be m. So I is going from 1. So A is m by n. And x is in Rn. So sum over I is going from 1 to m, and the sum over j is going from 1 to n. Okay. So then I'm going to have, I'm going to take xj, move it out here, and then I have a sum over I on the inside. Aij. But this is the sum of the absolute value of all the entries that are in column J. So if I replace this by the maximum column sum, then I can pull it out of the sum over J. But that's 1 by the assumption. So the one norm of AX is bounded above by the maximum column sum. Now, that only tells me that the one norm of A is less than or equal to that maximum column sum. I need to find a vector X that gives me equality here. So if X is set to the capital J's column of identity, or the maximum column sum is from a capital J's column. So I find the index that maximizes the sum. If my board is here, then the one norm of AX is equal to max column sum. So the idea is first you show that the matrix norm is less than or equal to whatever expression you want. Then you show that there's some vector X that gives you equality, and you're done.
Is that supposed to be the norm of A, or should it be norm of AX?
Actually, I for one is correct, because the certainly AX, but then but since norm of A is equal to the max of this, then yeah. is written up far more cleanly in the notes. Especially the conclusion of it. All right. Okay. Any questions about what happened here? Okay. If we're establishing an upper bound for the norm, we want to make sure that the expression we're getting is not just an upper bound, but the least upper bound. So we establish equality. So next. Okay. All right, so that's the one. The infinity norm is a maximum row sum. I take the maximum of I going from 1 to m. The absolute value of all the entries in that row. Then that's the infinity norm. And the way you prove that, I won't do it here, but the way you prove that is we're using a very similar argument to how this one norm was established. So in fact, you could say that the infinity norm of A is equal to the one norm of a transpose. Two norm, not so simple. So, if I consider a definition, what the definition would give me, a maximum over all unit vectors in the two norm sense. The two norm of AX. Actually, this is two norm of AX. Okay. So what I'm going to do is to show you what it would be. It would also be the soup over all non-zero x, two norm of AX divided by two norm of X. Okay, so we're actually going to use a little bit of multivariable calculus to arrive at a formula. Okay, so I'm going to define a function g of x to be equal to the two norm of AX squared over the two norm of X squared. But that would be the same as X transpose A transpose AX over X transpose X, because in general, the two norm of a vector squared is the same as the dot product of a vector with itself. Okay. So if you have a function of several variables, this is a function of all the components of X. How do you find the maximum? You want the gradient to be equal to 0. And I won't go through all the differentiation here, but like you'll see something like this in the next chapter. The gradient of G is equal to a 0 vector if the following holds, that A transpose A times X is equal to two norm of AX squared times X. But the thing is, here we have matrix times vector equals scalar times vector. That's an eigenvalue eigenvector relationship. So X is an eigenvector, and Oh, do I have a mistake here? Of course I do. Oh. No, it's not a mistake. Okay. And for this to be true, and thankfully it does say so in the notes, assuming X is a unit vector, in which case this scalar here is the eigenvalue. But in that case, that's also the value of g of x. And g of x is exactly what we're trying to maximize. So g of x is maximized by x being the eigenvector corresponding to the largest eigenvalue of A transpose A. And g of x, what we're trying to maximize is the 2 norm of ax squared, but the maximum of that would be the 2 norm of A. So that tells me that the 2 norm of A, which is the maximum over all unit vectors of square root of g of x, okay, that is equal to the square root of the largest eigenvalue of A transpose A. Okay, I need to clarify. Yeah, I'm talking about eigenvalues of A transpose A, because it's A transpose A times a vector equals scalar times a vector. Does that make sense? I feel like I'm not sure, but okay. So let's make sure for everybody. Maximized when x is an eigenvector. The eigenvalue in that case is the value of g of x. We want that to be largest. That's why we take the largest eigenvalue of A transpose A. And g of x, when maximized, is the 2 norm of A squared. So we take the maximum square root of g, which is square root of the largest eigenvalue. Okay. Thing is, that's not an easy thing to compute. And for a 1 norm infinity norm, we have a pretty simple formula, just adding up certain entries of A, the absolute value. Not so for the, we're actually going to learn at the end of the semester how to compute the largest eigenvalue. This is a symmetric matrix. And when we learn about singular values, this is the same as the largest singular value of A. We'll learn about singular value decomposition in chapter 4, and when we get to chapter 6, we'll learn about the algorithm for computing it. So that takes some work. So if you need the matrix norm, you might want to consider using one of the others, like a 1 norm or the infinity norm. And there's one other matrix norm of interest that is easier to compute than the 2 norm. It's called the Frobenius norm. It is not a natural norm, though. It is not induced by any vector norm. I guess you can think of it as, since it's unnatural, it's a zombie norm. But very simple formula. We use the subscript f. And all it is we take a square root of the sum of all the entries of the matrix squared. So it actually is like if you took the matrix and thought of it as a big long vector with m times n components, and then took the 2 norm of that. That's the Frobenius norm. Okay. Okay, all these norms are equivalent, all the matrix P norms are equivalent, and a Frobenius norm is equivalent to these other, P norms, so. We have this relationship that the Frobenius norm is greater than or equal to the 2 norm. And it's less than or equal to square root of n times the 2 norm. And there are similar relationships among the other matrix P norms.
Question. So this Frobenius norm, can that only be applied to square matrices?
Oh, no, because there's a mistake. To be yeah. I think it's even saying at a point, A is n by n, and yeah. Okay, now. Now I can finally get to the concept for which I wanted to talk about norms in the first place, after spending literally an hour on norms. The condition number. So in MATLAB, there's a function called norm, and you can use that to compute the normal vector or matrix. By default, it will compute the 2 norm of whatever vector or matrix you give it, but you can use the second argument to specify a different norm if you want it. Okay, now. So you want to know how sensitive is a problem AX equals B to changes in A or B. So this gets to what's called conditioning of a problem. And we're going to talk about conditioning for AX equals B, but for numerical algorithms in general, you don't want a situation where a small change in the problem leads to a large change in the solution, because that means you can't trust the solution. You're bound to have small changes, because what if the data for your problem, like your A or your B, come from the same measurements that could be erroneous? And if a problem is that sensitive, that error could really throw things off. And the really pernicious thing about conditioning is it's not a property of the algorithm you apply to a problem, it's a property of the problem itself. If you have a badly conditioned or sensitive problem, it will pose difficulties for whatever method you throw at it. So we hate ill-conditioned problems. The trouble is we're stuck with them. So to get an idea of how sensitive is we're going to examine this problem. That's a perturbed problem. A plus epsilon capital E x of epsilon is equal to B plus epsilon little e. This deals with what is called backward error analysis, which states that it's an assumption that the computed solution of a problem such as AX equals B is the exact solution of a perturbed or nearby problem. So X, our solution here, depends on the parameter epsilon, where epsilon is the notion of how much the problem has changed. So X of 0 would be referred to as the exact solution. of AX equals B. That's what we're really after. Okay. Now, for convenience, I'm just gonna refer to this as just plain old X. Okay. It's the exact solution. Okay, so, what I'm going to do is find out how much the computed solution, the perturbed solution, deviates from the exact solution by finding an upper bound for this ratio of norms here. So this is the relative change in X of epsilon. So how much, so if a problem is changed by a little bit, by how much does the solution change relative to the size of the exact solution? Okay, now for this, we need an expression for X of epsilon. Now what I can do is take this perturbed equation and rearrange it in such a way as to isolate X of epsilon. So I'll just write it off to the side here. So A X of epsilon is equal to B plus epsilon E minus epsilon capital E X of epsilon. And then what I can do is multiply both sides by A inverse. So X of epsilon is equal to A inverse B, but that's X. So the exact solution plus epsilon. And then I have A inverse little e minus capital E X of epsilon. Now, it's not an explicit definition of X, formula for X of epsilon, but it gives me an expression for X of epsilon minus X. That's what I need. So if I subtract X from both sides, I can use what's left in here. So now I have A inverse little e minus big E X of epsilon all over all of X. Now, I've not specified which matrix norm I'm using. I'm just using generic properties of matrix norms, including sub-multiplicative property that will apply no matter what norm I'm using. Okay. Next, what I'm going to do is I'm going to do a little add subtract trick here. So in here, I can replace capital E X of epsilon with capital E times X, as long as I compensate for it over here. Okay. Okay. Yeah. Okay. Now, using various properties of norms, like in particular triangle inequality. Okay. All right, so I have epsilon multiplying everything throughout. Okay, so now I'm going to have norm of A inverse, norm of E over norm of X. Okay. plus norm of A inverse times norm of E. And then I have norm of X, but that cancels out with norm of X below. Okay. Yes, that's what I want. Okay. And then then I have R times, I'll define R in a second. X of epsilon minus X over X, where R is defined to be the norm of epsilon A inverse E. Okay. And we assume that R is less than 1. So as long as you choose epsilon sufficiently small, it will be less than 1. Okay. Now notice, oh, I goofed here. I need to put this square bracket over here because epsilon is already accounted for in the R. Okay. Oh, dang, running out of time. Notice on the left side of all this, I have norm of X of epsilon minus X over norm of X. I have the exact same thing over here, but multiplied by R. So I can take this term and move it to the other side. And now I'm going to have norm of X of epsilon minus norm of X over norm of X times 1 minus R, which I can now divide by. Now I have norm of X of epsilon, X of epsilon minus X over norm of X is less than or equal to 1 over 1 minus R. And that's why I needed to assume that R is less than 1. And what's left here is I have epsilon, and then in what's inside, I have a common factor of A inverse. Norm of A inverse. And what I'm going to do is multiply and divide by the norm of A. So I put norm of A here. And then in what's left, I have norm of little e over norm of A, norm of X, plus norm of capital E over norm of A. Now, norm of B equals norm of AX, the B is AX. This is less than or equal to norm of A, norm of X. But since norm of B is less than or equal to norm of A, norm of X, that means that 1 over norm of A, norm of X, what I have here, is less than or equal to 1 over the norm of B. So now I have this expression, 1 over 1 minus R, epsilon, kappa of A, I'll define in a second, and then we have norm of little e over norm of B, plus norm of capital E over norm of A, where kappa of A is defined to be the norm of A times the norm of A inverse, and that is the condition number. Okay, of A. That's supposed to be a Greek letter kappa. All right, so in English, what does all this say? It says that the relative change in the solution when you perturb a problem a little bit, the relative change in the solution is bounded by this factor, whatever 1 minus r, times the relative change in the problem, because this is a relative change in the right-hand side, if we times epsilon it is. And then this times epsilon is a relative change in A. But all of that is amplified, just like my voice is right now, is amplified by this condition number, kappa of A. So that's where things can go badly. That whatever change is made in the problem, however small it might be, if a condition number is large, in other words, if A is ill-conditioned, could lead to an outsized change in the solution. The condition number is always greater than or equal to 1. It's when it gets really large, like 10 to the 10 or worse. That's when you really can't trust your solution to AX equals B that MATLAB or whatever other tool is computing for you. All right. Any questions about this? I know I've just hit the end of time. Questions from Peter Gallery online? Okay. So so the condition number is large, we say that A is ill condition. That's what we want to avoid. Now, the condition number actually depends on which norm we're using. So if I want a condition number like in a 2 norm, then I would take a 2 norm of A times a 2 norm of A inverse. So in general, it should be specific of which norm you're using. But if a matrix is ill-conditioned in a certain norm, it's going to be ill-conditioned in any other norm too, due to norm equivalence. I have an example in the notes of like a case of a 2x2 system where you have a matrix, you change it a little bit, and then you solve both systems, and you find that even though A and B only changed by a little bit, the solution changed by a ton. So, okay, I could try it to happen that way, but it can happen, and we have to be aware of that. The only other thing that's point I bring up in the notes is that okay, I'll stop soon, I swear. But this is an important point about the condition number. So you can think of the condition number I want to make sure this is stated reasonably precisely. Okay. The condition number indicates nearness to a singular matrix. So in other words, if a matrix is very badly conditioned, its condition number is very large, that means that A is very close to a singular matrix. So you'd only have to change A by a little bit, and the matrix would be singular. Okay. Now, the condition number is a more reliable and remember, singular means non-invertible. Not to forget to indicate that as a synonym for that. It's a more reliable indicator of near singularity than the determinant of A. Because you learned in your first linear algebra class that a matrix is invertible if or non-singular if and only if its determinant is non-zero. The trouble is the determinant is influenced by the way the matrix is scaled. whereas the condition number is not. So there's an example, there's an example in the notes where you have a matrix that is badly conditioned somewhat, and it's actually quite close to a singular matrix, even though the determinant of a matrix is nowhere near zero. And you can also have cases, especially by scaling, where a matrix has a very small determinant, so you think, oh, this matrix is almost singular. But it turns out it's actually well conditioned. So, so really, in terms of like having a measure with that makes sense geometrically, it's the condition number, but indicates near singularity, not the determinant. Okay. Yeah, I've run long enough. So, okay. So that concludes chapter 3, but definitely send homework questions. In case I haven't made it clear, especially since we have some taking my class for the first time. I'm putting some deadlines to try not to fall too far behind. I know I can give hints where needed. So, so on Thursday, we'll start chapter 4 on least squares problems, where we no longer assume A is square. Okay. Yes, I did remember to record, thank God. I've already forgotten once this semester.